Swayam Prabha. Digital India. Educated India.
We learned how to do the modeling, right? And first, added mass radiation damping excitation force already kind of confusing. Now I talk about two impulse response. One is radiation impulse and also excitation force impulse. And we always say, wow, this system is not causal. How come, right? And you wouldn't imagine that way. Before the hammer hit your mass, the mass is moving. But for the wave, that is true because the interaction of wave propagation and the mass. Okay, so this how long it will interact depend on the size. Okay.
Sir, thank you for a nice lecture. I have two queries. I just split the questions in the two different parts. First one, in many papers when I read, people are not using this force impulse thing. They are trying to calculate f of t at a particular omega. Let's say that omega may be a natural frequency of that particular structure. So they take that particular natural frequency, what is a force, and they multiply with some sine function or cos function. Then they make it a sinusoidal forcing term, excitation forcing term. So here what we are using in the infinity added mass is which means there is some at infinite frequency. What is added mass? So that value it comes. So one added mass I have, but when I'm trying to calculate for a radiation impulse function, so I have to consider all the data points on all the frequency. So it is like in the equation, I am using all the frequency data points for a radiation impulse thing, but I am using only one frequency for excitation force.
Okay.
So this understanding I need to know that.
Okay. So there are two reasons here. One reason is frequency domain, everything can be understood easier, right? So as I said here, and you have frequency dependent parameter. You just imagine that x is capital X times e j omega t, one frequency, right? And you say when you do the simulation and look like you look into one frequency, but you use all the frequencies to calculate the impulse, to calculate the radiation force, right? The reason is, now look into this equation here, right? And the reason you use one frequency because the excitation force, if you measure the displacement, you use the displacement as input. So this part is complicated. It's non-causal, right? In time domain simulation, you want to make it simple. This is why most of the paper, your literature you read, in this part, they didn't use wave input. They just use force input. Okay. Okay. You use force input because this is non-causal for the convenience. And however, when you calculate the radiation damping term here, using convolution, you find you need to consider all the frequencies. Make sense? Right? You use all the frequencies so that you can calculate the radiation force impulse. And here you use single frequency, time domain. Okay.
Professor, to follow up with the question that student has raised. I mean, I also agree that many of the places we happen to see for the force for one particular frequency, that's what, I mean, it looks good on a paper front, that's okay, but on a realistic, the output that what we are looking for, the question is like for a given site, if we know what is the for example, for the site specific HSTP is given, so you know what is the spectrum for that, right?
Yeah.
So basically we can get the force spectrum as well, correct? So that force spectrum we can do the inverse Fourier transform to get as a function of time. So can that be used as a excitation force that in the equation that is shown? See, the question is generally in papers we happen to see for a particular frequency. Even when in our classes when we did for all this small coding, all that's what we did. But I'm just curious to know, is it okay to use the force spectrum? The inverse of inverse Fourier transform we can use to get the as a function of time, and that can be fed as an input. Can that be worked out?
It can be worked out, and many people are doing that way, right? And you want to say overall performance of one wave energy converter in one particular site, right? And you do all this single frequency calculation, right? After you do them, you remember what I said, the power map, significant wave height frequency, right? Each point is single frequency, right? You can do the time, the frequency domain simulation. Frequency domain simulation, you calculate the power. After you calculate the power, you time the probability, right? This case only happened 5% around this year. This part is 0.3% around the year, right? Then you add all this single frequency together, then you get overall performance, right?
Okay.
Is this clear, right? So in that way, you can do all this single frequency calculation, and with integration of power map, you can evaluate the system. However, some other case, you say, wow, this power map, how many cases? You need to, you have very extensive calculation. You may calculate 100 cases, right? You want to do the time domain simulation and, okay, generate, for example, this wave is very irregular wave, then you want to say what the time domain, the performance look like, right? So this, you can use WEC Sim to do that time domain, you get sense. Make sense, right?
To summarize our discussion, is it so for a given site, if we are knowing what is the scatter table, HSTP table, for a given site, I think I remember you were showing about that as well, right? What is
let me bring up the previous lecture, the slides, and so this kind of fluid basic. That is what we did here, and right. So this this wouldn't allow me to show that. Okay, so why I cannot show that? Okay, that is simulation we did, right? And then each case you have wave amplitude and also wave height, and man, so this figure is kind of full. So this file is not open, right? Let me open it again. Let me close this and open. Okay, so I don't want to use full screen. Full screen, the system will not work well. So here, this power matrix, right, percentage, right? Each case, we calculate a single frequency case, then time the probability, then we get a sense how much energy to generate a year, and then we eventually get the calculation. The calculation takes a lot of time, right? And you also don't know, you get average power output, but you don't know what the time domain look like, right? And you want to get a sense about time domain, for example, the wave energy converter. Okay, you want to you want to simulate the time domain, and you can use time domain simulation with the probability with the, let me say that way. You are given this one, you can calculate the like this one, Okay. If we are given this spectrum, right, this you mirrored in the frequency, in this certain area, you generate a time domain function. There's your wave amplitude input, right? Wave amplitude input, you calculate excitation and calculate the radiation force. Then the time domain simulation, you can see what's look like. Okay.
Sir,
Yeah.
just for a little clarity, like in that Cummings equation, what the input we are giving in the excitation force with respect to time is, you are using some Fourier series, right?
This one.
That
Okay.
that f of t, f e f t, f suffix e f t, that excitation force term.
This one?
That's that one, first one.
Okay.
That one.
And this one.
That is a my frequency domain output. So I am using all the frequency data, right? All
Yeah,
the
you
frequency
are-
force data, and you are using there, and you are applying that.
Right.
I want to convert. This is let's say you are analyzing the regular waves.
Okay.
The waves is a regular wave analysis, so the regular wave data is there.
Regular case, you don't need this, right? It's just one frequency.
Just one frequency. So
Yeah.
if I want to convert that frequency omega into some spectrum.
Okay, let us say that one, this is already this frequency domain that has a 1 or 0.5. This is your excitation force, right? It's already one frequency, right?
Yes,
Yeah.
Professor. I mean, again, we are. So we have this output, for example, right? Based on the diffraction analysis, we got this outcome. So now, if I am going to this, let us take this as an RAO square. Like if I RAO square into the input spectrum, I get the response spectrum for the force, right? So I get the response spectrum of the force, and that I will do inverse Fourier transform to get as a function of time. Can that be fed as an input for the first equation, right hand side, first component?
You can.
Yes.
Yeah.
So
Yeah.
that's what we wanted. Okay.
Yeah, you can. Yeah.
Okay. Because in papers we happen to see much of the time they take a single frequency. Though for other activities we depend on all the range of things for impulse response and all other things. But then for force alone they are just working out for a single one.
Yes.
So but it doesn't. The outcome looks very nice, but in reality it's actually not. It's kind of you will get an irregular outcome basically, right? So
Yeah.
that's what we wanted to get clarified. So we can use it, right?
Right.
Okay.
Right.
Thank you, sir.
Okay.
Sir, can I ask?
Yeah, please.
Can I use the?
You want to use the board? You want to write?
Yeah.
Yeah, go ahead.
So you talked about this keeping the force like before it is going,
Yeah.
and we are taking from this center point.
Yeah.
So this, let's say it's O and something, some amplitude.
Yeah.
And so what I wanted to ask is like, instead of considering one single point, because it's a meters long, many meters long.
Right.
So can we have something like some points here, so 1, 2, 3, 4, and some D1,
Yes.
D2, and some this some weight function, some weights. Can we do like that?
You can do that. That is, some people actually put multiple sensors on the point observer, so that they can measure the force distributed around
Maybe
that.
if we put some weight function based on the distance from the center,
Right.
Can we do that?
You can, but it's complicated.
Okay.
Yeah, you understand, right? And you can measure the wave at each point, then calculate, right? And you know wave at each point, then calculate the force at each point, then integrate together.
So
Right.
better stick to the assumption and assume like some error, like something.
And like India National Lab, they put the buoy into the water, and then the buoy, around the buoy, they put another sensor, pressure sensor, right? Yeah.
So this might be helpful, but it's very complicated.
Yeah. Any other question? Again, I want to say, we talk a lot about theory, right? As I said, I want to emphasize the physics, right? If you understand the physics, then you can have your own idea, right? How to do something new, right? If I just give, okay, this frequency dependent parameters, right? Then you understand, right? Okay, I can understand the paper, but it's hard to come something more creatively, right? And a lot of ideas are very simple, right? Like 2 papers I show you. One here today I show you 2 papers. One is the cup shape, and use this shape to create added mass, right? And then reduce the frequency. Another thing is radiation damping is not damping. It's just wave energy propagate out, right? If you understand that, wow, it's not damping, can we take advantage of that, right? Then you can create some array. The energy loss from one structure can be energy gain to another energy converter. Then this is why you get 1 plus 1 is much larger than 2. I don't know, you just now you get his point or not. His point, okay, you said the force come before, come to the center, we interact with the buoy, right? And his idea, I put on all those sensors around the buoy. Each location I measure the wave, then I calculate the force. I don't need to worry about is causal, non-causal or not. It's doable, but at the cost, right? You need another sensor to measure. Or you think that way, just out of the box thinking. You put a buoy, another buoy, right? And you can do the preview control, right? You can measure the buoy, the mirror outside the buoy act as sensor, right? Then before that buoy, the wave come to your buoy, you already know the wave is coming. You can predict the force, right? Or you can just put a sensor in the wave transmission direction, you can predict that, right? So, and here I didn't explain, today I didn't explain the power in the system yet, right? And for the wave energy converter, another paper say, okay, we want to take as much as power possible. You just think about physics. The buoy is moving up and down, right? Then what's the idea to maximize the power to the system? You guys play swing set, right? With case swing set, if this person move towards you, right? You let that hand draw, go back, and when it go another direction, you push that, right? Come again, swing set example, okay, right? Swing set like that. And when you want to make this more faster, right? When it come towards you, then you don't get force. When it goes that direction, you push that, right? So, because force time velocity is the power, therefore, for wave energy converter, and first impression you want to achieve is your excitation force and the velocity will be in phase. In that way, every time the wave excites the system, they give energy to the buoy, right? When you do this thing, every time when you have interaction, you give energy to the system, you get more power input to the system, right? Force and velocity in phase. So this is the input part. And later, on Monday, I'm going to teach you, okay, this most time is true, but it's not always true. Sometimes you get maximum power to the system, output power may not be maximum, the electricity. If you have some friction, some damping in the system, then even you get maximum power to the system, a lot of energy get dissipated by other non-perfect element. If you have non-perfect element there, then maximum input power doesn't mean maximum output power. So this is why I need a core design concept. And let me say it way. After that, we discussed so much about hydrostatic stiffness, right? Hydrostatic stiffness, rho g time cross section area. Time cross section area, right? Okay. So a lot of time, the stiffness is too large. If stiffness is too large, there's no resonance, right? So excitation and wave excitation frequency is, for example, like this one. Your wave excitation frequency is very, very low, right? Then you need what you can do is the stiffness is too high. If spring mass damper, the spring stiffness is too high, what you will do? Yeah, I cancel the stiffness. I create a negative stiffness. If my stiffness is 100, right? Now it's too high. I want to have 10. I create a negative stiffness, negative 90. How to create a negative stiffness? Right, use active control. Right, active control. You sense the velocity. You sense the displacement. You have negative time this type of displacement. You create a negative stiffness. Right, this is how you achieve how you maximize the power output, right? You think about the box negative stiffness spring damper or spring, you cannot achieve that. Okay, I can use control to achieve that. What's the risk? Negative stiffness, you use spring, negative spring. Ideally is fine, but if you have imperfection in the system, right? For example, power electronics, how to create such kind of force, there's efficiency there, right? So another thing is, what if there's uncertainty, right? We say our vibration system, nothing is linear, right? We have linear assumption. You want to cancel that. What if in some situation, then you cancel too much? The system is not robust, they become unstable, right? If you become unstable, you can not get energy, right? So there are a lot of things you can think about that. Okay, we are going to discuss more. The course is a little short. There are a lot of things I want to teach you, but we don't have enough time. Just now we talked with Dr. Vijay, say what we are going to teach you next lectures, right? And as I mentioned that, and to Dr. Vijay, we are going to cover a little bit about environment problem. We are also going to cover a little bit about cost problem, right? So we are engineer, but we need to consider the cost. Eventually, your system design is perfect system, ideal system, but tweak a pencil, then no one will buy, it will be, everything just stay in the lab, right? So when we design the system, we also need to consider the environment impact. For example, the PTO part, and if you have some PTO, there's water, there's operation oil inside. If there's water, not water, liquid leakage, then they create pollutions, right? And another thing is this system you put in the water. What if there's some noise, right? Or you have electromagnetic impact to the marine mammal, or the type of thing we need to consider, right? So, and PNL Pacific Northwest National Lab, Dr. Corbin, she did excellent work looking into the marine environment impact to the environment. So there's a state of science report about marine environment impact. Okay. So, and when I teach course at the University of Michigan, I have such kind of lecture. We have more time to cover, right? Or sometimes we also invite them for the guest lecture. So in this course, probably such kind of important topic, I want to just get your mindset, and but I only give you very, very short part, 15 minutes, whatever like that. Okay. What else you guys want to learn, right? Tell me what else you want to learn, then we have time to adjust our lecture notes, then to best meet your need.
Professor, one more question. In Cummins equation, how can we give the nonlinear stiffness force?
Okay, so Cummins equation itself, we didn't, it's not a nonlinear force. You can add another term. For example, if you consider this one, right? Mouse, okay. Consider this one, you can add, for example, drag damping, right? And or you have spring, Morin stiffness, you can add that, yeah.
So, Professor, I have another questions related to the Cummins equations. Like we are using added mass at infinite frequency. Could you please explain why we are taking added mass at that particular frequency? Why
Okay.
not all the range of the added mass?
Okay, that means, why, for example, this part, why you have this term, right? You just think, okay, I write radiation force as function of incentive wave, right? You have wave input, you have some parts, right? This part is added to balance, okay. Otherwise, you wouldn't have this part. So to balance the equation. So how people figure out, and I'm not the first one, okay. So I guess people, when they say, okay, I have wave excitation, I have some function that they may, when they try this one, they don't have this term at the beginning. Later they find that this equation cannot be balanced, so they add the term. Yeah. Thank you. So we have not an equation, we talk about that, but really I want to get the physics insights crossed. Then you understand the physics insights is more important, right? And however, with this physics insights, you can write your own equation, right? Create your own knowledge. Yeah. Other question? What else you guys want to know? Again, I said this lecture initially I prepared for with the assumption, and people have background of fluid and vibration, whatever like that. And this way, when we talk about that, is for the people who stay college 2 years, it's above head, it's okay. Yeah. And you get the idea and you think more. Then when you read the paper, you say, yeah, I know this concept.
Sir, everyone, can we have a group photo now? Since we have time. And also I need.
If there are no other questions, we will close out this session and we'll have a group photo now.
Okay.
So this is part of the Jan. Every day, I mean, they are asking for it, so that's what
Yeah,
time.
and I'm available for individual meeting. You want to chat with me and have some research idea or something you want to know about United States or talk about politics stuff. I'm available to chat with you guys.